Learning to count, you may have used your fingers to help you, possibly even your toes. But eventually, you ran out of digits and had to use other tools to help you enumerate. The field of combinatorics continues this process, providing us with other methods for counting collections of objects. For example, consider your WSU password. Even a simple 5-letter password has over 1 million possibilities. Your WSU password has a minimum length requirement of twice that. It requires lowercase letters, uppercase letters, a number, a symbol. I wouldn't be surprised if it started asking for an emoji at some point. Counting the number of possibilities that this generates without the framework combinatorics provides would be near impossible. I like to use combinatorics to count in a more two-dimensional sense. Before you lies Pascal's triangle. In its rows, you can find the coefficients and the expansion of any binomial expression. So take x plus y. X plus y to the 0th power is 1. That's the top row. X plus y to the 1st power has coefficients 1 and 1. That's the next row. X plus y squared gives you the following row, and so on, all the way down. Pascal's triangle is famous for a pattern it contains. Every number in the array is a sum of the two numbers directly above it. So 15 is a sum of 5 and 10. There are other patterns as well. For instance, the sums of certain slant diagonals will give you the Fibonacci sequence. My interest lies in thinking about these patterns in a different way. I'd like a pattern that gives me 0 out, that would annihilate the array. In Pascal's triangle, this means I'm going to take the negative of every entry and then add it to the 2 entries above. So I'm going to take negative 15 and then add it to 5 and 10. I can imagine taking this pattern and overlaying it anywhere on my array, and I would always get 0 out. My research focuses on taking this sort of zeroing out method and applying it to different types of arrays, particularly for what's known as Riordan arrays. The study of Riordan arrays is a very fast-growing field. It has applications not only in combinatorics, but in graph theory, networks, even data analysis. Pascal's triangle is the canonical example of a Riordan array, and it originally motivated the field in the 90s. Now, Riordan arrays are traditionally described column-wise by their generating functions, but they can also be characterized by a pattern that we can observe in their rows, just like we saw here today. This pattern can take many different forms, even be infinite. My research focuses on exploring the corresponding zeroing representation, characterizing it, and determining the requirements for its existence.